Hello everyone, I'm Dhiraj Madan. Welcome to this new lecture in the course series on electrostatic conductors. Today we'll be looking at the topic of electric field outside conductors and the idea of electrostatic pressure. So basically consider a conducting surface, a conducting electrostatic surface with a varying charge density as sigma as a function of x, y, z. Okay, so basically there is this charge density which can vary, okay, with point. So what we have is consider a conducting surface with variable charge density sigma as a function of x, y, z. So now we know that firstly, inside the conducting medium, the electric field is zero. Firstly, secondly, outside the medium, the field is perpendicular to the surface. But the question is that how much is that field, right? So, or how to compute the field. And it turns out that there is a very simple expression for that electric field outside the surface in terms of the charge density. So let's compute that today. Let's compute that now. Okay. So when you have a conducting surface, okay, so what we'll do is that we'll consider a small cylindrical box. Okay. And let's look, okay, with a radius of r and height which is almost negligible, almost going off to zero. Now we assume that we are choosing this cylindrical surface such that one surface has electric field E1, this is outside the conducting medium, and the other part E2 lies within the conducting medium. Right. So basically, so E1 and E2 are the sort of electric fields on these two circular patches of the spherical surface, and E1 is the electric field on the upper patch which lies outside the medium, and E2 is the electric field in the lower patch in this figure, and which lies inside the conducting medium. So basically assume a cylindrical surface with uh, with electric field E1 on top surface, which is outside the medium, and electric field is E2 in inner surface, which lies inside the conducting medium. Okay. Now, how much is the flux of this? So the flux is given by E1 perpendicular minus E2 perpendicular dA. Okay, so what I'm assuming is that dA is the area of the top cylindrical of the upper and the lower surfaces. Okay, and the walls have almost zero height, so they don't contribute to the flux. So the net flux over here is essentially so I'm assuming that both E1 and E2 are in the same direction. So in the bottom part, the contribution of flux will be minus of E2 perpendicular dA. This must equal the net charge enclosed over epsilon naught. Now, how much is the net charge enclosed within the cylindrical box? Well, the charge density is sigma, then the area of this this top box is dA, so this charge enclosed must be sigma dA over epsilon naught. Okay. So essentially what you get is that E1 perpendicular minus E2 perpendicular is sigma over epsilon naught. So the difference between the electric fields in the upper and the lower patch, right, if there is a surface of charge density sigma, that is sigma over epsilon naught. And note that until now, we haven't used any property of the electrostatic conductors. So this is essentially a very general result which is true for any conducting surface and any charged surface of with charge density sigma, the whether it's conducting, non-conducting, it doesn't matter. The difference in the electric fields which in the upper and the lower parts is always sigma over epsilon. Okay. Now in our case, in case of conductors, what happens is that E2, right, the electric field inside the medium is zero, right, which implies that E2 perpendicular is also zero. And we have seen that E1 perpendicular minus E2 perpendicular is sigma over epsilon naught, which means that E1 perpendicular is sigma over epsilon naught, which means that the net electric field E1 is sigma over epsilon naught n cap. N cap as in directed away from the surface perpendicular to it. But this result is also this equation, right? E1 perpendicular minus E2 perpendicular is sigma over epsilon naught. This is also true for any charged surface, even if it is non-conducting, right? In general, like meaning that even if the surface is not conducting, we have that E1 perpendicular minus E2 perpendicular is also sigma over epsilon. But in this case, in general, we can also have parallel components along the surface. But the difference in the perpendicular components is this much, right? We cannot say that, E2 perpendicular is zero or even parallel and E2 parallel are zero. All that we cannot say. And remember, you have already seen something similar for infinite plane sheet also. For infinite plane sheet, we see that the electric fields in the upper and the lower side are essentially E1 is how much? Sigma over 2 epsilon naught n cap, and E2 is minus sigma over 2 epsilon naught n cap. So n cap is essentially, I'm just taking along the upper direction. And now we can see that E1 perpendicular minus E2 perpendicular is sigma over epsilon. But this result, if you remember, was only when the sheets were infinite. Then we could see that they are essentially sigma over 2 epsilon naught n cap and minus sigma over 2 epsilon naught n cap. This is not true in general, for finite patches. In the conducting case, when we computed the result, we computed it for any finite patch, and this difference result, this is true in general, whether the surface is finite, whether the surface is infinite, whether the surface is conducting, non-conducting, this is always true. Okay, and right, so this is always true, but specifically for conductors, we have that outside the conducting surface, the electric field is sigma over epsilon or n cap, and inside it's zero. That's specifically only for conductors. And in infinite plane sheet, when we saw the result, we again saw that, well, it's true again for, we are not assuming whether this was conducting or non-conducting, but we made one assumption, which was that this was infinitely spreading and uniformly charged, right? So here essentially there is no assumption of uniform charged. Okay, so true for infinite sheet which is uniformly charged. Okay. Now, although when we talk about this patch, right, we see that the difference in the electric fields is always sigma over epsilon naught. Okay, but the net contribution to the field could be due to other charges also. It's just that the charge density sigma will cause a difference of fields along the two sides to be of sigma over epsilon naught. That's something we can always say. But in general, the electric field which you will be observing will be due to that entire thing, not just due to the patch, right? So the patch, what we can say is that the difference is just sigma over epsilon. So actual contribution to E1 perpendicular, E2 perpendicular can be other than patch also. From now on, we are now okay, but the net effect is that this difference is sigma over epsilon. Now coming back to the idea of conductors, the question is that if you want to compute the force which is experienced by a given patch, right? Then how do we do that? So that's the idea of electrostatic pressure, which we will discuss. So the question is as follows, which is that how to compute the force experienced by a conducting surface. Okay. Now, in order to compute the force, what we do is that we first try to compute the force experienced by a patch, right? So let's look at the same thing again, right? So we had this sort of this surface, right? We drew a cylindrical surface, right? And we saw that outside the electric field was sigma over epsilon naught n cap, and inside this electric field was zero. But the thing was that this electric field is of course due to the patch, and it has some other components also. So we need to know how much is the other components and how much is the component due to patch, right? Because the force experienced by a patch will only depend on the other component, right? The patch will not exert the force on itself. So essentially outside the conducting medium, we have that sigma over epsilon naught n cap is essentially the electric field due to this patch plus the electric field due to other components. So other component could be this sort of the remaining conducting surface, it could be some external charges, whatever, right? We don't care about that. What we know is that this is sigma over epsilon naught n cap, but then there are these two contributions to it. Whereas inside, what we have is that the net electric field is zero, but there will be contribution due to due to this there's contribution to the electric field due to this patch, which is now in the opposite direction, right? Because now this sort of surface is like we'll be creating that electric field in the opposite direction inside the patch and outside the patches. But if I just move some very small epsilon distance, then the electric field due to the remaining components will remain unchanged. So now if I sort of average this out, what I get is that this E other, which I'll now compute, will be sigma over 2 epsilon naught n cap, right? So I add these two equations, I get 2 E other is sigma over epsilon naught n cap. So E other, right? So this is the electric field due to all charges other than this patch, right? So that is going to be sigma over 2 epsilon naught n cap, and the electric field due to the patch, right? So if I now substitute this E other in the first equation, that is also sigma over 2 epsilon naught n cap. But note that this E patch, right, this will change the sign as I move across the surface. So on one surface it will add with E other and give me sigma over epsilon naught n cap. On the other hand, this E patch will be in opposite direction inside the conducting medium and will cancel it out. So that will give me a net electric field of 0. So thus what we have is that the net force experienced by the patch is how much now, right? So basically there is the external electric field of E other, right? And how much will be the force? Force is Q times E. And how much is Q? Q is the charge on this patch. How much is the charge on this patch? So sigma is the charge density. Sigma dA is the charge. So the net force is sigma dA times E other. Okay. Now how much is this? So E other is going to be sigma times sigma over 2 epsilon naught n cap dA, right? So which is sigma square over 2 epsilon naught dA n cap. Okay. So the force per unit area. So this is essentially for a small patch of area dA. This is the force. So force per unit area along the direction perpendicular to conductor is sigma square over 2 epsilon. So basically on every small patch, I am getting a force of sigma square over 2 epsilon or dA along the direction away perpendicular to the surface. And this is so in every such patch, this is the net force per unit area, right? So this is essentially the electrostatic pressure. This gives me a net force of integral over sigma square over 2 epsilon naught n cap dA. So I've earlier we talked about 5 properties of electrostatic conductor. So firstly is that electric field inside the conductor is 0. Charges inside the conducting medium are 0. Then we saw that all points are at equal potential. We saw that there is no on the only place where the charges can reside are on the surface, and the electric field along the surface is 0 outside the conductor, and along the, so basically the only component of the electric field on the surface is perpendicular to the surface away from it, right? So outside the conducting medium there can be electric field, just outside the surface is perpendicular to the surface and away from it. How much is it? We have now computed finally, that is essentially sigma over epsilon naught n cap, okay, which has two components. One is due to the patch, which is sigma over 2 epsilon naught n cap, and the E other, which is also sigma over 2 epsilon naught n cap. How much is the force which the patch experiences? That is only due to the other component, which is sigma square over 2 epsilon naught n cap dA. If I want to compute the net force, I need to integrate over the entire conducting surface, which is this result. Now, we'll end this lecture with one particular problem which appeared in JEE Advanced 2010. So let me do this problem. So consider two conducting uniformly charged hemispheres which are held together by an external force F in equilibrium. And we need to compute the minimum force F, which is so needed. Okay. Essentially, what we have is that there are these two hemispheres. And essentially, each of these is now, uh, they have some charge density sigma, right? And a radius of r. And I'm using a force to keep them together, right? So in this diagram, they are slightly separated because I just wanted to show you the how these two hemispheres are, but I'm applying a force to keep them together. Okay, these two hemispheres are supposed to be together. Now I need to compute the total uh, uh, force which needs to be applied. Right. So let's compute the force which is required to hold one single hemisphere. So if I want to compute that force, the idea is that, okay, so at every point, right, there is a pressure which is being experienced, which equals sigma square over 2 epsilon. This is the pressure which is experienced at every patch over here. Now, if you look at it, right, so basically whenever you have a patch which makes an angle theta in the above part, there is a corresponding patch which makes the same angle theta in the lower part. So essentially the components of these forces, right? So they, of course, these forces are along the direction perpendicular to the surface, which is the normal to the surface. They are going to have two components. So first is the vertical and the horizontal components. So here we can see that the vertical components of the above and the below parts of this single hemisphere, they'll cancel in pairs. So the only components which will remain are the horizontal components. So how much is that? So what we can do is that we can look at all the points which are on the same sort of a ring which makes an angle theta, right? With this line passing through the equator, right? So basically this angle is theta, and there is a ring wherein all points they make an angle theta with respect to the horizontal line passing through the center, right? So all of them, we are going to only look at the horizontal parts, and those are going to be equal, right? So how much is the horizontal part along this line, along this ring? So essentially, the force on every patch is sigma square over 2 epsilon naught. Out of this, the component along the theta direction is sigma square over 2 epsilon naught cos theta. And if I look at this ring, right? So this ring, how much is the sort of area of this ring? So the area of this ring is going to be, this radius of this ring is going to be r sine theta. So this is 2 pi r sine theta is the perimeter, right? And this ring is going to have some thickness also. This thickness is r d theta. Right? So d theta uh, is the change in angle, and r is the radius. So r d theta is the thickness of this ring. Right? This is d theta, and this is r. So this is r d theta. So the area of this ring is 2 pi r sine theta times r d theta. And every point experiences a pressure per unit, which is force per unit area of sigma square over 2 epsilon naught cos theta. So this is the net force which is experienced by this ring of width d theta. And if I integrate theta from 0 to pi by 2, that will give me the net force. So how do we do that? So sigma square over 2 epsilon naught I can take outside, and this pi r square also I can take outside, and I'm left inside this thing. Okay, so there is sigma square, yeah, pi r square, and inside the integral I'm left with 2 sine theta cos theta, which is sine 2 theta. Sine 2 theta d theta. Theta goes from 0 to pi by 2. So overall, this integral happens to be sigma square over 2 epsilon naught times pi r square. And integral of sine 2 theta is minus of cos 2 theta over 2, right? And theta goes from 0 to pi by 2. Okay, and cos of 0 is 1, cos of pi is minus 1. So overall, I'm going to get 2, which cancels with 2 in the denominator. So the pressure is sigma square pi r square over 2 epsilon naught along minus I cap, right? So that is the force which is experienced to the left. So I need to apply an equal force on the right. So that's the force I'm going to apply. Sigma square pi r square over 2 epsilon naught to the left hemisphere and same amount of force on the right hemisphere. Then that is going to keep them together, right? So that will cancel the electrostatic force they are experiencing. Essentially, we just applied the idea of electrostatic pressure, which we have seen, sigma square over 2 epsilon naught. We needed to compute the areas of these patches and integrate them together. What we did was that we took all the patches on the same ring, which makes the same angle theta with the line which goes horizontally to the left. And with that, we just integrated, we computed the area of each ring and the force per unit area along the ring on the x-axis on the horizontal part. The vertical parts, they cancel out, and then we just integrated over all the angles theta to just add up the contribution of each ring. So that's the final result which we have gotten. Just to summarize for today's lecture, what we learned is that the electrostatic field inside the conducting medium, we knew it was 0. Outside the conducting medium, we know it was perpendicular to the surface. How much was it? We computed it today, which is sigma over epsilon naught n cap. We computed the net force experienced by every patch, which is sigma square over 2 epsilon naught times dA, or the pressure, electrostatic pressure, which I'm going to call that is sigma square over 2 epsilon. Right? So that force is obviously always perpendicular to the surface. So that was it for today's lecture. Hope you liked that. Thanks, and yeah, let me do subscribe to this channel and like the video to get more such content. Don't forget to press the bell icon, and yeah, we'll keep making more such videos. Hope you like them. Thanks. That's it for today. Goodbye.